Welcome to our Quantum Deep Dive.
Hi there.
Today, we're taking on a topic that honestly sounds like something straight out of science fiction, but it's rapidly becoming reality.
It really is.
We're talking about hybrid quantum classical clustering for data analysis. This deep dive is built on some really comprehensive insights from Yorgo Schneppet's excellent essay.
Yes, it's fascinating work.
And our mission today is pretty straightforward. Cut through the jargon, unpack how this groundbreaking approach is set to revolutionize how you make sense of the, well, increasingly complex and, frankly, often overwhelming amounts of data surrounding us.
Absolutely overwhelming sometimes.
Think of this as your shortcut to understanding the absolute cutting edge.
Absolutely. And, clustering itself, it's such a foundational technique in data analysis.
Right.
It's basically the art of finding hidden patterns, grouping similar data points together, and crucially, without needing pre-labeled examples. But as data sets just balloon in size and complexity, or let's say traditional methods, they hit some very real, very frustrating roadblocks.
Yeah, I can imagine.
So this deep dive will reveal how combining the mind-bending power of quantum computing with these established classical techniques offers a genuinely promising path forward. Delivering those aha moments. You need to navigate this information deluge.
Okay, let's unpack this then. We talk about data constantly, but what exactly is clustering and why is it so vital in our modern data-driven world? I mean, from the photos on your phone to how companies market products to you, it seems like it's everywhere.
It truly is, yeah. At its core, clustering is really about sorting.
Sorting?
Yeah, imagine you have this massive pile of unlabeled items, right? Say, thousands of different kinds of fruit.
Okay.
Clustering algorithms, they're like these incredibly clever sorting machines that can look at each fruit's characteristics, its color, size, taste, maybe density, and automatically group them into categories like apples, bananas, oranges, even if nobody told the machine what an apple was beforehand.
Oh, okay. So it figures it out on its own.
Exactly. It's used in super diverse fields.
Yeah.
Image processing, for example, it helps systems recognize objects or segment parts of an image.
Right.
In bioinformatics, it might classify gene expression patterns, maybe to understand diseases better.
Wow.
In marketing, well, that's obvious, it helps companies profile customers or pinpoint target audiences. And in network security, it's crucial for spotting anomalies or preventing fraud, like identifying unusual groups of transactions.
That makes sense.
The goal, always, is to find the best possible groups so that everything within a group is very similar and everything in different groups is very different. It's basically a huge optimization puzzle.
So when we talk about those sorting machines, the classical algorithms people use, like I've heard of k-means or hierarchical clustering, what are the go-to ones and where do they start to, show their age? Where do they stumble?
Yeah, good question. The most widely used is probably k-means. It's wonderfully efficient, simple to understand too. You basically pick a number of groups, K, and the algorithm tries to find the best centers for those groups.
Okay.
But it's got a couple of Achilles heels.
Yeah.
It's quite sensitive to where you started off, meaning different starting points can lead to different results, maybe not the best ones.
Ah.
It can also get stuck in what we call local minimum. Think of it like rolling a ball down a hill, right? And it gets stuck in a small dip instead of reaching the very bottom of the valley.
Right, not the actual lowest point.
Exactly. Then there's hierarchical clustering. This one creates a really beautiful tree-like structure of nested clusters, showing how different groups relate to each other at different levels.
That sounds useful.
It is, but the downside.
Yeah.
It gets computationally very expensive very quickly. Like often the complexity scales with the square of the number of data points.
Oh, wow.
Yeah, so for truly massive data sets, it becomes practically impossible. Just takes way too long. And finally, maybe dbScan. This one's fantastic for finding oddly shaped clusters and, importantly, ignoring noise or outliers in your data.
Okay.
But its effectiveness relies heavily on you, the user, carefully choosing the right parameters. And that can be pretty tricky sometimes.
This raises, I think, a really important question. What are the fundamental challenges these classical methods face when you're dealing with the truly massive, intricate data sets we have today? Why might you, listening now, feel overwhelmed trying to make sense of it all?
Yeah, the core challenges really highlight why we need new tools. First, there's just scalability.
Right.
As data sets grow, the time these classical algorithms need, it often doesn't just grow linearly, it can explode. almost exponentially sometimes.
Yikes.
K-means, for instance, can get bogged down incredibly quickly as the number of data points or maybe the complexity of each point as dimensions expands, which leads directly to the notorious curse of dimensionality.
Ah, okay. What's that exactly?
Well, imagine trying to find patterns in data that has not just 3 or 4 attributes, but hundreds, maybe thousands.
Okay.
In these really high-dimensional spaces, weirdly, everything starts to look equally far apart from everything else.
Huh.
It makes it incredibly hard to distinguish meaningful clusters. It's like trying to find unique snowflakes in a blizzard. They all just blend together.
Gotcha. So distance loses meaning.
Pretty much. And as we mentioned, issues like getting stuck in local minima and being sensitive to how you start them off, those plague many of these iterative algorithms. So you might not find the absolute best solution, just a good enough one.
Right.
And these limitations, they're precisely why we're exploring entirely new approaches, like quantum.
So if classical methods hit this fundamental roadblock, basically, to understanding the sheer vastness of modern data, here's where it gets really compelling. How do quantum computers offer a solution? What are these quantum principles that are supposedly so revolutionary?
What's truly fascinating here is that quantum computers don't just process information faster necessarily. They process it differently. They leverage the bizarre, counterintuitive rules of quantum mechanics.
Bizarre is right.
Yeah. There are 3 key principles really at play. First, superposition.
Okay.
Imagine a light switch that isn't just on or off, but can be both on and off at the same time until you actually look at it.
Whoa.
That's kind of like a qubit, a quantum bit. It can exist as a 0, a 1, or a combination of both simultaneously. This ability, it lets a quantum computer explore many possibilities at once. Huge parallel processing power.
Okay, superposition. What else?
Second, entanglement. This is even stranger, maybe.
Uh-oh.
2 or more qubits can become intrinsically linked. So linked that the state of one instantly influences the other, no matter how far apart they are.
Instantly, like faster than light.
Well, it doesn't transmit information faster than light, but the correlation is instantaneous. Think of it like 2 perfectly synchronized coins. If one lands on heads, instantly the other also landed on heads, even if they were tossed miles apart.
Okay, that's weird, but useful.
Incredibly useful for complex calculations. This linking allows for really rich and interconnected information processing.
So superposition and entanglement.
Combined, they enable what we call quantum parallelism.
Right.
It means a quantum computer can perform calculations on many, many inputs simultaneously, unlike classical computers that basically process things step by step. It's like evaluating an entire library of books at once, rather than reading them one by one.
That sounds like a superpower for complex problems.
Yeah.
How do these principles translate into actual algorithms that can tackle optimization challenges, like finding the best clusters?
Yeah, exactly. Because many clustering problems can be framed as optimization tasks, right? Finding the best way to assign data points to clusters to minimize some cost function. That's where powerful quantum algorithms, like the quantum approximate optimization algorithm, or QAOA,
QAOA.
and the variational quantum eigensolver, VQE, come into play.
UQE. Okay.
QAOA is actually a hybrid quantum classical algorithm. It's particularly well suited for these combinatorial optimization problems, where you have a huge number of possible combinations and need to find the best one.
Like clustering.
Precisely. It frames the challenge in a way a quantum computer can understand, then uses this tunable quantum circuit with alternating operations. A classical computer then fine-tunes these operations iteratively, kind of guiding the quantum computer towards the optimal cluster assignments.
So they work together.
Exactly. And VQE, while it was originally designed for quantum chemistry problems, it also applies to optimization. It helps us find the lowest energy state of a problem, which usually corresponds to the optimal solution. Both are really about finding the best path through this dizzying number of possibilities.
But we hear so often that quantum computers are still in their very early stages. What's the reality of today's quantum hardware? And what does this NiceQ era actually mean for these really promising algorithms? Can we actually use these powerful quantum algorithms right now for, big problems?
That's a really important question to address, yeah. It brings us squarely to the current phase, which we call the NiceQ era.
NiceQ.
Stands for Noisy Intermediate Scale Quantum.
Okay. Noisy.
Intermediate.
Yeah.
It means today's quantum computers are still quite limited. They have a limited number of qubits, typically dozens, maybe up to 100 for general purpose machines. Though some specialized ones, like D-Waves annealers, can have thousands. but for specific problem types.
Right.
Crucially, they're also highly error-prone. They're noisy due to environmental interference and something called decoherence, and they lack robust error correction.
Or they make mistakes.
They do.
Mm.
It's like trying to do complex calculations on a very unreliable calculator. So, while these fantastic quantum algorithms are being developed, these hardware limitations mean that purely quantum solutions for truly complex real-world problems, they're currently infeasible.
Ah.
And this is precisely why hybrid approaches, blending classical and quantum, are so critical right now. They offer a practical path forward today.
Okay, so this is where it gets really innovative then. If purely classical methods have limits, and purely quantum methods aren't quite ready for prime time on their own,
Yeah.
how do we combine them to get the best of both worlds? What's the motivation for these hybrid approaches?
The motivation is crystal clear, really.
Mm-hmm.
Classical methods struggle with the sheer scale and those traps, the local minima we talked about.
Right.
While quantum computers in their current NISQ state are limited by quota count and those high error rates, so hybrid methods are designed to intelligently divide the labor. Think of it that
Yeah.
way. They use classical computers and procedures for tasks they're good at. Initial data prep, simplifying the data, controlling the overall process.
For management stuff.
Exactly. Then the quantum algorithms step in to do the specific, computationally intensive, heavy lifting, the optimization steps. The parts where quantum computers, even noisy ones, might offer an advantage in exploring vast solution spaces.
Okay.
It's the symbiotic relationship, leveraging the strengths of both, allowing us to tackle problems that maybe neither could solve efficiently on its own.
So how do these variational quantum circuits, VQCs, specifically apply to clustering? And like a really practical question, how do you even get your classical data, your images, your spreadsheets into a quantum computer? It speaks in qubits.
That's a core challenge, absolutely. A key concept here is variational quantum circuits. For clustering, first you need to translate your classical data points into quantum states.
The encoding step.
Exactly, the encoding. Think of it like teaching the quantum computer a new language. There are different ways to do this. You might encode data by adjusting the amplitudes of the quantum states.
Okay.
Or by converting your data into binary form and mapping that directly to qubit states, or even by using the angles of rotation gates within the quantum circuit.
Different dialects for the quantum computer?
Kind of, yeah. Once encoded, these quantum states are fed into a parameterized quantum circuit. That's the VQC part. This circuit performs a series of quantum operations. We take measurements to get, say, initial cluster assignments.
Okay.
But the magic happens when a classical optimizer then iteratively adjusts the circuit's parameters, the dials on the quantum circuit, if you will.
Ah, the classical computer tunes the quantum one.
Precisely. Constantly refining those parameters to get closer and closer to the optimal clustering solution.
Yeah.
It's this continuous feedback loop between the classical and quantum worlds.
Okay, that makes sense. And what about quantum annealing, like the D-wave systems use? How does that fit into hybrid clustering? Is it similar?
It's a distinct approach, but also very powerful, particularly for certain types of optimization problems called combinatorial optimization.
Right.
For clustering, using an annealer, the problem is essentially rephrased into a form the annealer understands, often called a quadratic unconstrained binary optimization problem, or QUBO.
QUBO, okay, another acronym.
Yes, lots of acronyms. Imagine mapping your clustering problem onto a complex energy landscape, like hills and valleys.
Okay.
The quantum annealing system starts in a state that explores all possibilities simultaneously, like being everywhere on the landscape at once due to quantum effects. Then, by slowly changing its quantum temperature or field, it gradually settles, or anneals, into the lowest energy state.
The bottom of the deepest valley.
Exactly, which corresponds to the optimal cluster solution for your QEBO problem.
Neat. And where is that being used?
Is being actively explored for tasks like segmenting images, grouping genetic data in bioinformatics, and even, as we mentioned, rapidly identifying unusual patterns for fraud detection in financial transactions.
So it's definitely a multi-step process then, this hybrid approach. Could you walk us through the general architecture? Like, how would a system work from getting the raw data to spitting out those final neat clusters?
Sure. Yeah, it involves several key stages, typically. First, you always start with classical data processing.
Cleaning the data up.
Exactly. Cleaning, normalizing, and crucially, feature reduction.
Why reduction? Oh, the qubits again.
Precisely. Think of it as simplifying your data, stripping away noise, focusing only on the most essential information. Using classical techniques like PCA or TSNE, This is vital because remember, current quantum computers have limited qubits. We need to make the data as compact as possible.
Makes sense. Less is more for the quantum part.
Right. Second stage, the encoding of data into quantum states, using one of those methods we just discussed to translate the classical info into quantum language. Third, the quantum-based optimization takes center stage. This is where algorithms like QAOA, VQE, or quantum annealing perform the heavy lifting, figuring out the best cluster assignments based on the encoded data and the problem formulation.
The core quantum calculation.
And finally, stage 4, classical interpretation and validation. The quantum computer gives you an answer, maybe a set of qubits representing cluster assignments. You need to translate that back into understandable classical terms.
Right.
And then you use standard classical metrics like the silhouette coefficient or others to check the quality of the clusters, make sure they're meaningful and accurate.
Can you give us a concrete example how this is actually implemented with real-world tools, maybe like IBM's Qiskit or D-Wave Leap?
Certainly. Let's take IBM Qiskit. If you're using QAOA for clustering,
Okay.
you take your classical data points, formulate the clustering problem as the QUBO, that mathematical puzzle where the solution is binary.
Right, the QUBO.
You then build a QAOA circuit within Qiskit, designed specifically to minimize this QUBO objective function. You can run this circuit on a quantum simulator first, or if you have access, on actual IBM quantum hardware. The results from that quantum computation directly give you the optimized cluster assignments.
Okay. And D-Wave?
For D-Wave Leap, it's maybe a bit more direct for annealing problems. The clustering problem's objective function is formulated as a QUBO. You submit that QUBO to the D-Wave system via Leap.
And it just solves it.
Well, it performs quantum annealing. It intrinsically works to find the lowest energy state of that QUBO, and the result it returns represents the optimal binary assignments, which tell you how your data points should be clustered. It's about translating your problem into the language that specific quantum machine understands best.
So how do these hybrid models actually measure up against the traditional methods right now? Are they faster? Do they give better quality results yet? Are they living up to the hype, I guess?
Yeah, that's the million-dollar question, isn't it? Benchmarking is key. You compare both the runtime, how fast they are, and the quality of the clusters they produce, using those classical metrics.
Right.
Currently, for relatively simple cases, hybrid algorithms might actually be slower than highly optimized classical ones. Classical computing is really mature, right?
True.
However, the real promise lies in their potential for greater efficiency as quantum hardware matures, as qubit counts grow, especially for problems involving really complex global optimization, where classical methods often get stuck in those local optimas we talked about.
So they might find better answers, even if not faster yet.
Potentially.
Yeah.
Yes. Early experimental results are quite promising. QAOA-based assignments, for example, have shown results comparable in quality to classical methods, but with that added benefit of potentially finding globally optimal solutions where classical ones might fail. And D-Wave quantum annealing can also optimize cluster partitions effectively, though it still faces limitations with extremely high dimensional data. So, the verdict. While they're not always faster yet for all problems, they're definitely demonstrating the ability to tackle problems in a fundamentally different and potentially superior way.
So, okay, promising, but not quite there yet for everything. What are the biggest hurdles right now for these hybrid approaches? What's really keeping them from being used everywhere today?
The main hurdles really circle back to those hardware limitations of the NISQ era.
The noisy qubits.
Exactly. The limited number of qubits means we can only tackle relatively small data sets, or maybe highly simplified versions of real-world problems. The high error rates also mean our quantum computations aren't perfectly reliable. Getting accurate measurements can be challenging.
Right.
Then, from an algorithmic perspective, efficiently encoding large classical data sets into quantum states remains a significant challenge. It's like, how do you squeeze a huge amount of classical information into a small number of potentially noisy qubits?
The translation problem.
Yeah, it's a bottleneck. And many hybrid methods still rely on quite compute-intensive classical optimization steps, that feedback loop we mentioned.
So the classical part can slow things down too.
It can, yeah. It can introduce delays and bottleneck the overall process. These are all really part of the growing pains of a nascent but incredibly exciting technology.
So what does all this mean for you, listening right now, in the practical applications? Where can we expect to see this technology actually make a real difference in the, say, near future?
Well, the potential is vast, especially in fields absolutely drowning in data. Think about bioinformatics.
Okay.
Hybrid quantum clustering could, potentially, rapidly identify subtle clusters of genes with similar expression patterns. This could accelerate the discovery of biomarkers for diseases or even help optimize complex protein folding predictions. That could revolutionize drug discovery.
Oh, okay. Big impact there.
Huge. Or in the financial sector, it could precisely segment assets for better portfolio optimization, or, maybe more immediately, rapidly identify anomalous transactions for real-time fraud detection.
So, better investments, safer banking for you.
Potentially, yes. And in material sciences, maybe classifying complex crystalline structures to find new materials with unique properties, like high-temperature superconductors, or efficiently analyzing similarities between molecules to design new catalysts or better batteries.
So finding new stuff faster.
It's really about unlocking hidden insights in data that is currently just too complex for us to fully grasp with classical tools alone.
That's incredibly impactful. But looking further ahead now, what are the biggest challenges that still need to be overcome before quantum computers can truly revolutionize these fields? And what's the really long-term potential for, say, quantum AI?
The key challenges remain pretty clear, and they're significant. We absolutely need to scale the number of qubits significantly. We're talking moving from dozens or hundreds to thousands, maybe millions, for truly practical, large-scale applications.
Right? More power.
And we must drastically reduce those error rates. We need robust quantum error correction techniques so our calculations are reliable. That's a huge scientific and engineering challenge.
Making them less noisy.
Exactly. And we need to keep developing even more efficient ways to encode classical data for quantum processing, making that language translation much smoother and less of a bottleneck. Finally, better integration into existing IT infrastructures is essential. These quantum systems need to play nicely with the classical computing environment we already have.
Right, plug and play eventually.
Ideally. But the long-term potential is immense. Imagine error-corrected quantum computers solving huge optimization problems reliably.
Okay.
Improved hybrid architectures will seamlessly weave quantum algorithms into existing AI workflows. And scaling through cloud quantum computing will democratize access, accelerating research and development across the board.
This leads to a really exciting roadmap then.
Yeah.
How do we get from where we are today, this NISQ era, to quantum AI becoming a standard, maybe even everyday technology?
Well, if we look at a possible timeline, in the short term, say the next 1-3 years, we'll likely see improved quantum algorithms that are more resilient to noise, maybe cleverly designed to work around errors, plus new, smarter data encoding techniques. We'll also probably see more initial industry pilot projects, especially in finance and pharma, testing the waters.
Okay, baby steps.
Important steps, though. Then the midterm, maybe 3-7 years out. This could bring truly scalable hybrid architectures. The first quantum computers with significantly reduced errors, maybe the beginnings of fault tolerance, and perhaps a push towards industrial standardization of these systems.
Getting more serious.
Definitely. Then looking long-term, perhaps 7-15 years, maybe more, we can see quantum computers demonstrate quantum supremacy or advantage in specific practical clustering tasks, meaning they genuinely solve problems that no classical computer could realistically tackle in a reasonable time frame.
The point where it really proves itself.
Exactly. Quantum clustering could become routinely used commercially in certain niches. And this could lead to the emergence of truly quantum-enhanced AI, impacting everything from autonomous driving safety systems to deeply personalized medicine based on complex biological data.
Wow.
What's fascinating here is how this won't just accelerate data processing or find those elusive global optimal solutions. It might actually enable entirely new AI model architectures we can't even fully conceive of today.
This deep dive into hybrid quantum classical clustering, it truly shows the incredible possibilities when we combine the, established power of classical computing with the revolutionary, almost magical potential of quantum mechanics. It's clearly not just about faster calculations, is it? It's about solving problems that were previously just out of reach, pushing the very boundaries of what AI can achieve and what we can understand from the world's exploding data.
Indeed. And while the technology is still evolving rapidly, very much in development, the insights from Yorgo Schnepped's work, they highlight a clear and, importantly, a practical path forward, a way to start breaking through current data analysis barriers, even now.
Right.
And it really raises an important question for you, the listener. As these capabilities mature and become more widespread in the coming years, how will you leverage them?
That's a fantastic thought to leave everyone with. Thank you so much for joining us on this quantum deep dive.
My pleasure.
If you'd like to learn more about the fascinating work we discussed today, you can find the essay and other great information on Your O. Schneppet's website. That's schnepphat.de.
Yes, schnepphat.de.
Goodbye for now, and keep exploring.